Hi there, it's Paul Bamberg with the introductory video for Class 15 of Math 117. I'm sure you're all familiar with Riemann integration and quite good at the technique of it, perhaps a little weak on the definition though. So let me introduce the subject by giving you Dineen's definition of the Riemann integral, which is quite likely a bit different from any you've seen before. We start with a closed interval from a to b, and we break it up into a bunch of intervals that are next to one another. x1 is at the left end point, xn plus 1 is at the right end point b, and so we have subintervals going from x1 to x2, from x2 to x3. The last one goes from xn to xn plus 1, so we've got n of them. And arbitrarily in each interval, we choose a point xi bar. Could be the left end point, could be the right end point, it could be the middle. It could, I suppose, be chosen by a random number generator. It could be a point where the function has its maximum value in the interval. Nobody cares. We define the Riemann sum to be the sum over all the intervals of f at this arbitrary evaluation point times the width of the interval, which is xi sub 1 minus xi. There's no requirement that all these intervals be equal in width. The standard term for the largest width that you find is the mesh. So as the mesh gets smaller and smaller, in many cases these Riemann sums converge, and what they converge to doesn't depend on the rule for selecting xi bar. If that happens, we say that f is Riemann integrable on that closed interval. As a practical matter, it's standard to make the intervals all be equal in length, but there's no requirement of that. Now let's suppose we've got a bounded continuous function, the good case for Riemann integrals. In that case, we can get an upper bound on the Riemann sum that we're calculating by replacing f at the arbitrary evaluation point by the supremum of f on the interval. And we can get a lower bound by replacing it by lowercase m sub I, the infimum. In that case, we've defined what are ordinarily called the upper and lower Riemann sums, and the statement that the Riemann sums converge as the mesh goes to 0 is the statement that if we take the difference between supremum and infimum on each interval, sometimes called the oscillation multiplied by the width of the interval, and that quantity approaches 0 as the mesh becomes finer and finer, which is going to be the case if the function is continuous, then the Riemann integral is well defined. Since a continuous function on a closed interval is also uniformly continuous, all we have to do, in fact, is to let the mesh be some appropriate delta, and that's good enough for a uniformly continuous function to make the difference between the supremum and the infimum on an interval of length delta be less than epsilon. That means the sum I'm calculating here is less than epsilon, the upper bound of this quantity, times the sum of all the interval widths, which is b minus a. That goes to 0 as delta goes to 0, and f is Riemann integrable. When we defined the Lebesgue integral, we partitioned the codomain, and that was very convenient because when we were approximating the interval by a sum, the range of values that could be used got smaller and smaller as the mesh became finer and finer. That doesn't necessarily work in the case of the Riemann integral, where we're partitioning the domain, but it will occur if the function is continuous. For a discontinuous function, this difference between supremum and infimum could remain very large. The standard example of that is to choose a function that equals 1 for rational arguments, 0 for irrational arguments. In that case, no matter how fine you make the mesh, the difference between the supremum and the infimum is 1 in every interval, and the Riemann integral just plain doesn't exist, although the Lebesgue integral does. Now let me say a little bit about measure in general rather than probability measure. I'm going to do this by turning the issue into one of a calculation of expectation. We've got a function from a closed interval of the real numbers to the real numbers, and we can introduce a probability measure which, although it's not clear with the typeface that I'm using, is lowercase l for the interval from a to b. If f happens to be an integrable random variable, we already know how to compute its expectation, and if we multiply by b minus a, then we get the integral of f over this interval using so-called Lebesgue measure. If you look this up in Dineen, you'll discover he makes it a bit more complicated by considering an interval that may be just a subset of our closed interval. We can even make this work if the interval is all the real numbers, that is the closed interval from minus infinity to infinity. In that case, what we do is compute the integral from minus n to n, let n approach infinity, and if that limit exists, we use it as the value. Sorry about that. We're back. If f is continuous on the interval, which I remind you means it's also uniformly continuous, then we can calculate this Lebesgue integral as a Riemann integral. The Riemann integral of f from a to b is equal to the integral of f on that interval using Lebesgue measure, and the way you prove this is by using the dominated convergence theorem. You take your continuous function f and approximate it by functions that are constant on each subinterval. In that case, you end up with a nice simple random variable. You can compute the Lebesgue integral and show that you are actually calculating the same number as for the Riemann integral. So this d boldface m is nothing really special. It is the probability measure that we've been using all along, multiplied by the length of the interval from a to b, so that while the probability that your random variable lies in a to b is 1, the measure of the interval from a to b is the difference b minus a. The two things just differ by an overall constant factor. Now earlier on, you recall, we figured out a clever way of using a positive random variable whose expectation was 1 to define a new probability distribution. Let's suppose that we have a function f whose integral over the real numbers is equal to 1. Then we call this a density function for a random variable x if the following is true. The probability of the event consisting of all points in the sample space for which the random variable gives a value in between a and b, which is, by definition, the value of the probability function p sub x for that interval, is also equal to the integral of the function f over ab, with respect to our new measure, bold M. But there's a complication here. We can modify a function on a set whose probability is 0. We won't change the expectation, and we will still have a valid density function. So we have to choose a very specific value for the f that goes along with our new random variable x. I'll call it f sub x, and I can then say if that function is Riemann integrable, the probability function evaluated for the interval between a and b. Remember what a probability function does. It assigns a probability to a Borel set, is given by the integral of that specific f sub x from a to b. If we have another Borel measurable function g, and we can multiply f sub x, our density function, by g, and still end up with a product function that's Riemann integrable, then g of x is a new integrable random variable, and its expectation is calculated as follows. You multiply g by the density function, integrate over all of x. This is another example of the so-called law of the unconscious statistician, and most folks will say, this is obvious. The density function times dx, which is clearly the width of the interval, is the probability of being inside that integral. The value interval, the value of the function is g of x, and clearly we have to multiply those two things together and sum it up, but in the limit a sum becomes an integral, and therefore this formula is obviously correct. It's not quite that simple, but that's a very good mnemonic device. Now an example of a density function. We've seen only one of them so far, the exponential distribution, and that has a density function which is alpha times e to the minus alpha x for non-negative x, otherwise 0. The usual way of finding a density function is to start with the distribution function, which exists for any random variable. It's the probability that the value x, state that more precisely, it is the probability of the event, the subspace of the sample space, for which the value of the random variable does not exceed x. In many cases, this function turns out to be continuously differentiable. That is, it's differentiable and its derivative is a continuous function. So this derivative is a continuous density function. The continuity will guarantee that it is Riemann integrable. And a useful formula, which you will prove, is that if you make a new random variable by taking x, multiplying by alpha, and adding beta, there's a formula for the density function for this new random variable in terms of f sub x. The most important of all density functions is the one for the so-called normal distribution. If the random variable x has the so-called standard normal distribution, which we will be seeing a lot of, then the density function is 1 over root 2 pi times the exponential of minus x squared over 2. This is valid only because this density function, when integrated from minus infinity to infinity, has the value 1. The standard proof of this result is in Dineen. Why is this normal distribution important? It's important because of the central limit theorem. So let me finish up by stating, but not proving, the central limit theorem. We've got a sequence, x sub n, of independent random variables. They all have the same distribution function, and they therefore all have the same expectation and the same variance. There is, in fact, no requirement that x sub n has to have a density function. In particular, it could be a simple random variable, non-zero only for a finite set of possible values. And there's no requirement, contrary to what a lot of people believe, that its distribution should be symmetric about the mean. X sub n could, for example, be a function that has the value 1 with probability 0.3, has the value 2 with probability 0.7. No density function there. So here's exactly what the central limit theorem says. We've got these random variables. I'll refer to them generically as capital X sub I, and we will average n of them together. That is, add up n of them, divide by n. That makes a new random variable, y sub n. We then subtract the mean from y sub n, so we get something that has an expectation of 0, and we rescale by dividing by sigma over the square root of n. If we do that and take the limit as n approaches infinity, all of these constructed y sub n's will have a common expectation, and they will all have exactly the same variance as the individual x sub I. What the theorem says is not only that, the random variable that we get after we subtract off the mean and rescale has very specifically the unit normal distribution. In other words, if you ask, what is the probability that when you take y sub n, this average, subtract off the expectation mu, and rescale, that you get something that's less than or equal to x? The answer is you can compute that by integrating the density function for the standard normal distribution from minus infinity up to x. Now this statement unfortunately involves a new type of convergence, which is known technically as convergence in distribution. If we have almost sure convergence, convergence except on a set of measure 0, that implies convergence in distribution, but this doesn't work both ways around. So this convergence in definition in distribution does not imply almost sure convergence. Furthermore, if we don't have a density function everywhere, that is, if there are points where this distribution function f sub x has a discontinuity, then there is not necessarily any convergence at those points. We've got a couple of examples that you can work on in class that will illustrate this point. If there are such points, there's no density function, although we still have a distribution function. So to be precise, when I say that x sub n converges in distribution to x, what I mean is everywhere where the distribution function is continuous, I can say that the limit as n approaches infinity of the event where x sub n is less than or equal to x is the probability that the limiting distribution x sub omega is also less than or equal to x. Frequently, we have a situation where we have two sample spaces that are both just the real numbers. We have two sigma fields on these two sample spaces. They're both the Borel sigma field, and we have two random variables, x and y, that have density functions f sub x and f sub y, respectively. And now we can think about R2 consisting of pairs of values of the two random variables and ask for a specific subset in R2 in the plane about the event consisting of all points in the sample space where the pair of values lies in this set A. And we can calculate that by taking the product of the two density functions and integrating it over the set A. If you have taken a course in multivariable calculus, you have had a lot of practice in integrating functions of x and y over such sets. Now, if we have x and y, we can also form a new random variable by adding them together. The resulting sum has a density function too, and a famous formula, which I will not attempt to prove here, though it's done in Dineen, is that the density function for this new random variable z, the so-called convolution of f sub x and f sub y, can be obtained by taking f sub x times z minus y times f sub capital Y of y and integrating over y. If you look at this, you can convince yourself that it's almost certainly correct. What you're saying is, how can I have two random variables x and y whose sum is z? Well, if I pick a value y for one of them, the value for the other one has to be x minus y, and therefore it seems reasonable that multiplying these together and summing up all the possibilities, i.e. integrating, will give the correct answer. And with that hand-waving argument, I will conclude this little video.